Well, welcome to the introduction to PID loops, and it is an introduction, and I would like to obviously state that yes, we are planning a more advanced PID webinar in the near future. At this stage, we don't have a date set for it, but it is something that we're very keen to do, and we're starting to put material together even for that one while we were putting this one together. So we're going to cover the basics today, and in a future webinar we'll get more in depth, more into the meat of the subject of PID loops. So what exactly is a PID loop? Well, any time that you adjust what you're doing based on how things turned out the last time you did it, you're forming a PID or a feedback loop. We use them every day. Every time we, as humans, we are using PIDs and feedback loops continually. A PID loop is used to drive an input towards a set point and keep it close to that value by controlling an output of some kind. That's sort of putting it in very broad terms. So here's some human PIDs. The gentleman on the left on the balance beam is wobbling backwards and forwards. His set point or his concept is to keep himself on that balance beam, and he's looking at the horizon with his eyes, using his muscles and controlling himself to as a feedback loop, and every time he falls off he learns a little bit. Same with the lady climbing the stairs. When you fill a glass of water, the set point is obviously the water to the top of the glass, and then you are looking at that glass, so you're using your eyes, controlling your muscles, controlling the flow of water through the faucet, and ultimately closing off very gently the flow of water into the glass so that you don't overshoot and spill the water everywhere. So humans are basically just one big PID loop. Every time we pick up a pen off a table, we're doing a PID loop as we approach the table with our fingers very carefully so that we don't crunch into it. We grasp the pen and raise it to where we need to be. Of course, very common PID loop driving, as we adjust our speed, as we pull up to the lights, as we pull away from the lights. Everything that we do in a car just about is covered by a PID loop, turning the volume up, turning the volume down on the radio. We're adjusting it based on what we want it to be. Of course, once we're in the world of process automation, industrial automation, there are PID loops abound. We've just got two here. We've got a conveyor that's bringing maybe cookies into an oven, and we've got to control the speed of the conveyor such that the cookies are in the oven for the appropriate length of time, and we've got to control the oven temperature. It's got to be at the right set point so that we don't burn the cookies, but we do cook them all the way through. So there are just PIDs just everywhere in the natural world and where we're all familiar in the industrial automation world. What's Opto 22's implementation of it? Well, we have PID loops on all of our Pack R and controllers, and also our Ethernet brains and serial brains. We have 96 PID loops on each of those devices. So that's a lot of PIDs. It's a pretty high concentration. And the great thing about it, my background is healthcare. I was the Opto automation technician in a healthcare facility in Australia, and we used a lot of PID loops there because we're doing a lot of HVAC, but we also had swimming pools, chillers, boilers, electrical systems. There was just a lot of different PID loops. And so I really appreciated the fact that Opto had such a high density of PID loops per rack, so to speak, or per brain. I also appreciated that they were completely independent. I could have different scan rates for each of those 96 loops. I could use, if I wanted, I could use different algorithms between them, and we'll talk about that more shortly as we go along here. And we could also obviously have different tuning parameters. It was very important that we'd be able to tune each loop, and we'll talk about tuning here briefly as part of this introduction. So the one thing I do want to point out though is that the Pack S controllers, the S1 and the S2, don't have any PID loops in them. And the reason for that is because they don't have any I/O. And where there's no I/O, there's no need to have any PID loops. So it's only the PAC-R and the Ethernet brain and the serial brain that have the PID loops in them. One of the big advantages of having the 96 loops right down there in the brain is that they're completely independent from the control strategy. So you can have one chart or you can have 16 charts running in a PAC-R, and those charts can be doing anything you like and they're not going to affect the PID loops. The control process is done in the CPU and it's completely separate from the PID loops. They're going to be done in the I/O section of the brain, and they're completely independent from the control strategy. Being independent from the controller means that they're very fast. We can have very good speeds on all 96 loops, and they're not going to be affected in any way by anything that the controller is doing. Of course, they're not affected by a controller shutdown. So if you have a bug in your program and it sends the loop, it sends the controller into a bit of a loop and chews up 100% CPU of the controller or something like that, you're not going to have a problem with your PID loops. They're also very easy to configure. If you're using the configurator in Pack Manager, or more likely in Pack Control, you essentially just fill out the blanks. And so it just makes setting them up just so easy because we've stripped out all of the maths and we've just put in the parameters that you need to be familiar with. So let's get started. And one of the very first questions that seems to get overlooked a little bit when setting up a PID for the first time, and that is, I think, the very first question you have to ask and answer, and that is a PID loop really the most appropriate solution for your application? You know, PID loops have been around for a long time, PID controllers, integrated into PLCs and PACs, and so often it just becomes accepted that, well, we'll just put a PID onto it. But I think it's worth taking just a moment to step back and say, well, is that the most appropriate solution? Can some simple if-then programming do the job? If the tank is full, shut off the valve. There's no need for a PID necessarily if it's a digital valve. Can a mechanical device do the job? Again, sticking with our tank idea, can you use a ball valve on a float? And so as the float comes up, it turns off the flow. As the tank level drops, the float will drop and open the valve and start to open it. Is a mechanical going to be more appropriate? I mean, with a PID, you've got sensors, you've got to put electricity, you've got to run conduit, you've maybe some communications. So it's worth, I think, just taking a step back and asking and answering the question, is the PID loop the most appropriate solution? If it is, and you've decided that, yep, we really do want to put a PID loop in, I think the other one that's worth, the other question that's worth asking is your process in good mechanical condition? The PID loop is only going to be as effective as your mechanics. Now, obviously, in a brand new installation, in a new process, a new plant, you would want to hope that everything is going to be nice and tight and running very well. But if you're converting an old system, as we did a lot at the hospital, it was a very old hospital, and we had old pneumatic systems, and we'd be converting them to Opto. A lot of the time, we had to take a step back and really look at the mechanical condition of what it was that we were going to control. And a lot of times, you know, we had to change pumps, improve pumps, piping, one thing and another, in order to get the PID loop to even before we began to put the PID in. Otherwise, we were just fraught with problems. So your average PID loop configuration goes something like that. What I've listed on the left are required parameters. Pretty much every PID loop controller that you look at, and particularly obviously the Opto ones, are going to require the following information. And we're going to break all of these down and look at them one at a time, but we're looking at the scan rate, the input to the loop, and also the output we want to look at, and the set point, what you want the process to be at, which algorithm you're going to use in order to maintain that, and of course the tuning parameters themselves, proportional, which is often called gain, integral and derivative. And as I said, we're going to break each of these down and look at each one of them. So let's start with the very first one there that we listed, setting the scan rate. Your process really can't be tuned without it. You're going to need some value in the scan rate. Opto defaults to 1 second, I believe, 1 second, because you need to specify how often you're going to be doing the algorithm. And part of the setting the scan rate is understanding your process to the point where you can understand the dead loop time. So let's look at what this dead loop time is. What is dead loop time? Most processes will have some sort of delay between making a change and seeing the result of that change. If we look at the illustration on your screen here, we've got a gas valve and we're opening a burner, and as we open the burner we're going to put more heat into the bottom of the vessel, and obviously it's going to take some time for that heat to propagate through the vessel to our temperature sensor located about a third of the way from the top. We're not going to see an instantaneous change. As soon as we open the flame, within 0.1 of a second, we're not going to see that vessel increase in temperature. The dead loop time is the time between increasing, in this case, the flame, and seeing the change in the water temperature at the sensor location. And obviously, depending on where the sensor is located, is going to depend on the dead loop time. So you need to understand your process, and we need to be able to calculate that dead loop time. And the way we do that is by plotting a disturbance, and this is most easily done by using a chart, whether you're using the PID tuner helper in pack control, or if you're using pack display, you can set up a super trend and do this, but I do recommend that you do graph it one way or another, even using a paper recorder, so that you can see this curve and you can analyze it and look at it in detail after the event. But essentially what we do is we make a change in the output, we disturb the process, and we look for how long it takes from when we make that change in the output to when we see a change in the process variable. And that time is our system dead loop time. And that's very important to know, because what we need to do is we need to be able to set our scanner so that it does the calculation frequently enough to be effective. Now, we need to remember that unlike humans, where we are almost doing our PID loops at the speed of light, electrochemically our muscles and our minds are working very, very quickly, computers are a little more finite, and they're going to be doing the PID calculation at a set rate. Think of it like a heartbeat or a metronome, tick-tock, tick-tock, do the calc, do the calc, do the calc, do the calc. And that scan rate of when we do the calculation is what we're looking at here and finding out. You want to do your calculation at around 1/3 of the dead loop time. If you set it at the dead loop time, you're going to have a very sluggish PID, and it's going to be hard to tune because you're going to only be doing the calculation every time you expect a change, and so it's going to be constantly lagging. You don't want to do it too fast either. If you're pounding away at the PID loop, it's going to be doing the calculation very frequently to the point where it's not actually seeing a change for the scan rate that you put it through. So by putting the scan rate around 1/3 of the dead loop time, you're getting a good balance between doing it frequently enough to see any disturbances, but not slow enough that you're going to miss some disturbances, and not hyper fast to the point where you might be picking up noise or seeing every little change. So that's why it's important to know your process and to calculate that dead loop time. It's the first thing we need to do is set the scan rate. So the next thing we need to do is choose which algorithm. Opto offer 5 different algorithms. The velocity type C is relatively new. We've only added that about a few months ago. So previous to that we were offering 4 different types. So let's have a look at the different types. And we're going to start by looking at the velocity. because of the new type and also because of the importance of how these are calculated. I'm just going to select my spotlight here so that we can highlight some of these. Okay, there are some calculations that are common to both, and we've listed that at the top here. First of all, we calculate the span, the input and the outputs, and that just allows us to set up upper and lower limits and almost a little bit of a sanity check in the maths to make sure that we're not outside of these limits. The important parameter here that we calculate is the error, the process variable minus the set point. So going back to our tank, we're looking at the process variable, which is the temperature of our tank, currently what we're measuring, and then the set point is what we want the tank to be at. So it's what we want it to be is the ultimate goal. That's the whole point of the PID, is to make sure that our set point is reached and kept at. So we subtract our process variable from our set point so that we can see how far away are we from perfection. And that's put into the error. Now, once we get the error, this is where things change a little bit for our velocity algorithm type B and the velocity type C. We can see here that type B is subtracting our error from our previous error. And the previous error, remember we're doing the PID algorithm based on our scan time. So the previous error is going to be the previous scan, and our current error is right now when it does the algorithm right at this very instant. So we're going to take those two and put that into what we call the term P. For the velocity, you can see that we're actually taking the previous process variable away from the current process variable, and we're putting that into our term P. We'll get back to this in a minute. The rest of these calculations then are common to both velocity algorithms. So we're going to take our error, which we've calculated two different ways, times our scan rate, times our user enter tune I, and that's what we're going to do our term, our I term, and likewise with our derivative, and then ultimately the output gets calculated through, and we determine what the, going back to our tank, what the gas valve is going to be set at. Let's just take a moment here to really look at this velocity algorithm and understand why it makes a difference. If you have a look at it, the type B algorithm, we're going to see any set point changes. Okay, with the type B, as soon as we make a set point change here, let's say we want to change the value of the tank, and we change this value here, we're going to subtract it from our process variable, and it's going to end up in our error. For the type B algorithm, this error value then is going to change. With the type C algorithm, if we make a set point change, we're not going to see that change when we do the calculation, when we do the algorithm. We're only going to see any process variable changes. Now this will become really important and very significant when we get into the advanced topics webinar, because you want to be able to see the set point change when you're working with cascaded PID loops. We're not going to talk any more about that. I'll put it out there as a teaser for the next webinar that we get to. But I do want to point that out, that the type B, you're going to see set point changes. With the type C, set point changes are essentially going to be invisible. You, the user, could type in a set point change, and the PID calculation is only going to pick that up as the process variable through the error and through the I term, not through the gain. So that's our velocity. Let's have a look now at our ISA and parallel and interacting. Again, we've got some common parameters to both. You can see once again our error is the set point minus the process variable minus our set point. We've got two lots of commonality here. Up the top, the way our P term, I term, and D term is calculated is exactly the same for the ISA, parallel, and interacting. They're all exactly the same. Where they change, where they differ, is down here. Our gain is outside of our PID in the ISA. In the parallel, it's gains dependent, so that if you make a change to the gain, it's going to affect the others. And interacting, we split out our D term a little bit as well. So what does all this mean, and you know, can we break this down anymore and come up with some sort of hard and fast rule? Well, we can. We really can. It's relatively simple. If you have experience, if you have existing experience with a particular algorithm, then use that one that you know. If you're not got any experience with the velocity, ISA, the parallel, or anything like that, then simply use the default, which is the type B, velocity type B, where you will see a set point change, and build your experience on that velocity type B. Opto put those different PID algorithms in simply to help those people that have experience with the ISA, the parallel, the interacting. We put that in because we found that people that had experience with those algorithms wanted to be able to use them in Opto. All 5 type result in a PID algorithm or a PID response. They all end up controlling a process variable and making it match a set point. Okay, so it's not as complicated as, well, you might use a velocity if you've got flow, and you might use an ISA if you've got temperature, and use a parallel if you've got a convey. It doesn't work like that. They are simply there to ease those engineers that have previous experience with a particular algorithm. As a courtesy, Opto has put them into our firmware so that you can pick up and run with them, because you're going to have values that are comfortable, that are familiar to you. You're going to have an algorithm that responds for those values the way that you expect. So that said, obviously one of the very important things you want to do is try wherever possible to make sure that you use the same algorithm for all loops within your process. Okay? That way your operators aren't seeing one set of figures for one loop and a completely different set of figures for a different loop. And even if they're both temperature, it would be very confusing. Whereas if you use the same algorithms, the tuning is going to be very similar, and you're just going to find a lot more continuity. So yes, it's really that simple. Don't make it more complicated than it needs to be. If you've got experience, use that one. If you don't, use the default. Okay, let's now look at our PID in a little more detail. Proportional is going to be looking at our error, okay, our process variable minus our set point. And that's the offset between those, whether it's positive or negative, it's still going to be an error in the sense of our process variable doesn't match what we are trying to control. In the velocity algorithms, we're going to be looking for the change in the error. In the other algorithms, we're looking at different parameters, and you can go back and take a look at those algorithms and determine which one, if you're picking one from the start. Our integral is going to be looking at the error over time. We'll break all of these down a little more, but essentially the real key of the integral is it corrects any steady state error that results from the proportional. The derivative tries to predict where the control variable needs to be in the next scan rate. So it tries to anticipate whether you need to be increasing the speed of the PID or decreasing the speed. We've put in there use with caution. Well, yeah, we'll leave that at that, and because we'll talk more about the derivative and why you need to be a little more careful with it as we get to it. The proportional is often called gain. Some people call it P-band or P-term. Opto calls it gain. And quite simply, the larger the value, the larger the output for a given error. So let's have a look at this with the diagrams that we've got here. So when our gain is greater than 1, a small error here is going to result in a large output and a large output change. But that's when our gain is great. So you're going to start to pick up any noise in your signal. It's not going to take much of a change on your error side in order to get a large change, a large swing in your output. For a gain of exactly 1, then it's the same for the error here on the input as to what the controller is going to be doing on the output. So that's for when we've got a gain of 1. If we reduce the gain to be less than 1 but greater than 0, then you need a very large change here in the error before you see any change at all on the output side of things. So that gives you a bit of a feel. It's really straightforward. The bigger the larger the value, the larger the output for a change in the error. The other aspect about the proportional that we need to talk about is which direction the output is going to change. So let's use two easy to understand, easy to talk about: heating and cooling. So a positive gain gives a positive output for a positive error. A negative gain gives a positive output for a negative error. Yeah, confused? All right, let's break this down a little bit. So heating. Let's say we're cold. Okay, we can see here. This is where we are here, where the red dot is. We are below the set point. Right now I'm cold, so I have a negative error. What we need to do is we need to increase the amount of heat. Okay, we need to turn the heating up. We need more gas, more flame, more fire. The way we do that is by using a negative gain. By putting a negative gain on the calculation, we're going to end up with a positive output here, and we're going to get more heating. This is the direction that the seesaw is going to tip. If we use a positive gain over here at our cooling, see here we're above our set point. We're too hot. We need more cooling. The higher we get above our set point, the more and more cooling that we need. We need the cooling to be added down here. We need more snowflakes. So the way we do that is by using a positive gain. That way we'll get the seesaw swinging the correct way that we need. So that's the easiest way I found to remember it, is a positive gain gives a positive output for a positive error. My error here is positive. I'm over my set point. I'm too hot. I need a positive output here to turn up my cooling, and negative gain, when I'm below my set point here, I want a positive output to turn up my heating, and so we would use a negative gain on that. If we just use proportional control alone, what's going to happen is we're going to end up with a steady state error when we're using the velocity algorithms. If we go back and look at those algorithms, remember, it only calculates the difference between the process variable and the set point. And so if the process variable starts to level out, we're going to have zero error between the set point and the process variable. And so the output's not going to change. We can see here that wherever there's a difference between the two, or wherever the error rather is other than 0, we're going to see a change in our output, which is going to drive our process variable. But ultimately, once the process variable starts to level out and the error gets less and less and less, the output of our controller is going to be less and less and less until ultimately they both steady state. The problem is that this error between the two could be quite high, and we're not going to know what the error is because the set point and the process variable, when you subtract that, it's going to be 0, and the 0 error is what results in the 0 change. We're not going to see a change. So proportional control on its own is not very popular, and it had its use way back, but this very problem of not having the process variable meet the set point was the downfall for the proportional only control. The answer then is to bring in some integral. When we bring in the integral, it's going to multiply the scan rate and the current error. And so what's going to happen then is we're going to adjust for errors over time. That's what the proportional can't see on its own, but the integral, because it's looking at the error over time, it's going to eliminate our steady state error. So we can see when we do our calculation at this scan rate here, and then we do our calculation at this scan rate here, we're going to be able to pick up the previous or the difference in the error, and we're going to be able to push the process variable by changing the output to eliminate that error between the current process variable and the set point. So the integral is going to work with the proportional, and we're going to really start to get the PID function is starting to work together and give us exactly what we need. The derivative then is looking for the rate of change on the output, and it's generally used more with loops with long dead loop times. And I guess that's why I use so much of it at the hospital, because we were doing so much heating, ventilation, air conditioning, and we had rooms, large rooms, operating suites, rehabilitation rooms, large areas that did have a lot of dead loop time. We had one conference center that was up around 8 to 12 minutes, just depending on how they had the conference room sectioned off. It had some of those bifold doors in the middle. When the whole room was open, we had dead loop times of up around 12 minutes between when we changed the air temperature of what we were blowing into the room before we finally noticed that on the temperature thermostat on the wall. So you can see here that it's actually the slope that we're looking at. So we're looking at the this slope mathematically here, and the greater the slope here and here, whether it's approaching or departing, that's when your derivative is going to have the most effect. Where your process variable is very close to flat, whether it's at the set point or not, remember we're not worried about that. That the integral and the proportional is going to be taking care of this error between here. The derivative is simply looking at the slope, the speed that we're approaching the set point or the speed that we're departing away from the set point. One analogy that I like, which is why you need to use this with a little bit of caution, it's if you're looking for a modern day analogy, driving a car. Incorrect use of derivative is a lot like driving the car with one foot on the brake and the other foot on the accelerator. Now you can imagine how much wear and tear that's going to put on your car. You're not going to know whether or not you're driving down the freeway with the brakes nearly full on and smoking and getting very hot, and you're overusing your engine and you're using a lot more fuel than what's necessary. You can end up doing a lot of that with derivative. You can really cause your loop to work too hard and not be what we call critical dampening, because that's what we're looking at doing. We're looking at tuning the loop so that it's very efficient. That's exactly what we're looking at now, is tuning the loop. Tuning is required for every loop. I think now after you've been through this, as you can see that it is required. And we're going to be determining, the whole point of tuning is to determine the best values for P, I, and D. To begin tuning a loop, you really need to understand your process. This is very, very important. You need to understand what your goal is. Why is your set point such that it is? And what are you trying to control to maintain that set point? Also, when are you trying to maintain that set point? Because some processes have very, very different characteristics in startup and in shutdown. So we need to be really mindful of when are we trying to tune this loop. Are we trying to tune it for startup? Are we trying to tune it for shutdown? Or are we trying to tune the PID loop or tune the process for when the process is up and running and in its steady state? If the answer is all three, then I recommend that you keep your eye on Opto News and look out for the advanced tuning of the advanced PID webinar, because we're going to talk about some different techniques where you can use PIDs for different stages of your process. But it is important to understand your process. A poorly tuned loop is inefficient, obviously. It goes without saying it's going to cause a lot of wear and tear on your machinery, on your process, to the point where it may actually cause physical damage. If your loop is out of control and you have what's called increasing peaks, we can sort of see that over the side, even though there's a gentle rise in this particular screenshot. If you're getting increasing loops where the increasing peaks where the process is more and more and more out of control, you can actually do some damage. A real life example I've got of that is we had a pneumatic control at the hospital. It was controlling a steam valve for a heat exchanger, and it basically was just out of control. It was going from 100% open to 0% to 100% to 0%, and it was, because the steam has got a lot of energy in it, it was cracking and banging and causing the condensate pipes to rattle so much that the physical mounts of that pipework and the steam valve into the cement wall was actually cracking, and it was causing leaks in the system because it was banging that much. Also, a poorly tuned loop is going to affect your downstream processes and perhaps even the quality of that downstream process. If you're sending water temperature, for example, that's varying greatly, then anything that's going to require an even temperature is going to suffer, whether it's straight on quality or whether you're trying to tune those loops further downstream as well. They're going to be hunting against the water temperature that's going up and down from your main process. A well-tuned loop, conversely, obviously, is going to be very, very smooth process. It's going to be, in the case of our heat exchanger at the hospital, once we got the Opto hooked up to it and tuned that loop, you could hear the difference. It was just smoother. It was a lot more efficient. It's going to reach the set point a lot quicker with very little overshoot or undershoot. And it's going to be custom tuned for that process. And the benefits from that are quite remarkable. And this is what we're looking at here. We can see I've just taken a screen. We've got our graphic artist here to do up an ideal loop. We can see it's nice and steady, albeit above the set point here. We've disturbed the system by dumping some cold water into our heating tank. We can see that the PID has responded by opening our gas valve, which has caused eventually the heat to rise, and that has caused the PID to close down the gas valve. We've got a small amount of overshoot, and we get back to a steady state, and the gas valve here is at steady state. So it's just it's really it's a nice and satisfying process to tune a loop. So how do we go about that? Remember, this is introduction to PID loops, so we're just looking at this in overviews. There's three basic methods to tuning a loop. We have the open loop step test or step function response. We also can oscillate the process and have a look at that. And a third option, which is used quite a bit, is you can guess. And so let's cover these three before you fall off your chair laughing about the third method. One thing I do need to point out is that you really do need to understand your process. I'm sure the lawyers for Opto 22 want me to state that depending on your process, any or all of these methods of tuning may be quite dangerous. You need to understand your process. We keep coming back to that. It is very important. You need to be able to use the appropriate method for tuning for your process. So let's have a look at the open loop step test. Essentially what we do here is we put our PID loop into manual and we set our output at something other than 0, whether it's 5%, 10%, 40%, that's going to depend on the process, and again that's why you need to know your process. But set your output at a given percentage and wait for the process to settle down and obtain a steady state. Once it's got that steady state, you then make a step or a change in your output by at least 5%, preferably around 10% or more. So you can see that's what we've done here. We've set our output at something other than 0. We've waited for our process to obtain a steady state, and then we've made a step change in the output. Now what we're looking for is the process is going to have a certain amount of dead loop time. It may be very quick or it may be very long. We're looking for that change here, and we're looking then for the process variable to settle down and to steady out, flatten out here. Again, this is why it's a good idea to be able to use a graphic program to analyze this data so that you can actually take screenshots. At the hospital, we set up different pack display supertrends initially, and then once Opto provided the graphic tuning tool in pack control, we're able to use that because you can freeze time on that and you can print that out, and the cursors are really helpful as well. So what we then do is we calculate 63% of this curve, and we drop a line through that 63% curve point, and then we can start to extrapolate some data from that. And you can see what we're doing here. X is the percent of change in the output. Okay, so we're looking at the percent of change that we made here on our output. R equals the percent per minute change at the point of inflection, which is 63% of the change in the process variable. So from here up to here, 63% of that gives us our point of inflection. And D is where our tangent line intersects with our rate of change. Using those parameters then, we can then calculate for velocity some PI values and some PID values from that. Because the open loop step test is so popular, I've just taken another example here. This one doesn't involve the tangent, and so you might prefer to use this. I've used both the tangent method and this method and found both to be effective. Depending on the curve, it would depend on which method that I personally would use. So this one's a little easier because we're just looking at the process variable change versus the controller output change is going to give us our measurement gain. Our dead time, very simply, we've talked about that from when you made the change to when we started to see an output change. And our time constant, which is time for the process variable to reach 63% of the total change, this point here. So once we know these values, the change, 63% of the process variable change, we can then calculate some appropriate values. The only one that's a little bit different here is the derivative. Slow loops are generally any dead loop time of 10 seconds or greater is considered a slow loop. 10 seconds or less is considered a fast loop. So you would select whichever of those is appropriate for your dead loop time of your process. Again, it all gets back to knowing your process. The other method of tuning is to oscillate the process. What we do here is we put the PID into auto. We set the integral and the derivative term to 0, and then we slowly increase the gain until the process starts to oscillate. And then we very carefully and gently adjust that gain value until we get a nice constant oscillation out of our process. We don't want to see increasing peaks and we don't want to see decreasing peaks. We want to see a nice steady oscillation or ringing of your process. That ringing then is going to be here, this period between cycles, and that is the natural frequency of our process. So we'll know that because we can measure it on our graph, and then we know what gain setting we used in order to get the process to ring or oscillate naturally. Using those two parameters then, we're able to set. Of course, lastly, we talked about guessing. This is not as crazy as it sounds. Once you've got some experience tuning PID loops, you can actually get a feel just by looking at the curves. And essentially what we do is we put the PID into auto, we just let it run, we enter our reasonable values based on what experience we've got, and then we make a set point change. And this could be part of the process, the manufacturing process itself, or you could induce this yourself. And then you simply look at the response of the process to that set point change, and then we adjust the PID parameters by looking at these standard response curves. And we can go through the response curves and we can see whether or not we've got too low or integral, too much gain. This is what we're looking at here. It's come up too fast and it's undershot, and so on and so forth. You know, based on the descriptions that we've explained about the PID, we can see how these standard curves can be used. So the guess method isn't quite as crazy as it sounds, and it's certainly worth keeping in mind as you build experience tuning PIDs, particularly if they're very similar. I got quite good at guessing HVAC PID values based on the size of the room, the heating coil size, cooling coil size, boiler sizing and things like that. And I could get a room very close, very quick by guessing and then just looking at the response from there. With regards to configuring a PID loop, there's essentially two ways of configuring an Opto loop, and one is through Pack Manager. That's this screenshot here. This is particularly important if you're not using Pack Control and you're programming in C++, C#, Delphi, or any other language. You can look at all of the memory map addresses for each PID loop. You can see them all listed there for each of the parameters. So you can configure your loop in your software and get them up and running in Pack Manager very quickly and easily. With regards to Pack Control, you've got a lot more options. Becomes a lot more GUI involved. You can, what you see is what you get as far as the tuning wizard, and also just fill out the blanks. So it's a great graphical user interface, and it's very helpful for those of us that aren't programming in raw languages. When it comes time to save your tuning parameters in Opto, I just wanted to point out a couple of little aspects here. There is a Save Tuning button at the bottom of the graphical tuner, and it pops up this dialog box here, and it runs through. We've got our gain, our integral, our derivative, scan rate, feed forward, all of the parameters here except set point. And I just wanted to point that out because it's something that might be overlooked. Opto consider the set point to be a user variable, to the point where maybe it's coming from another PID loop, maybe it's coming from a calculation that you're doing as part of your process. The point is, we can't assume here at Opto that the set point is static and that you want that saved. So we don't save that, and so you just need to keep that in mind, that your process needs to be able to, your program rather, needs to be able to provide that set point to the loop. The other thing, it's only saved, the parameters are only saved to the strategy, and it points that out here. Saving these values to the strategy will require the strategy to be compiled and downloaded before entering debug mode again. So it's only saved to the strategy, and you do have to download your strategy in order to push those new parameters down to your I/O. This becomes important because if you've got, let's say you're using an Ethernet brain on a pack R and you lose network connectivity and then you cycle power to the Ethernet brain. Because you've lost network connectivity, when you turn the Ethernet brain back on, because the strategy can't communicate with the Ethernet brain, the PID loop is not going to be configured and it's not going to be running. So your Ethernet brain is just going to sit there. However, if you go into Pack Manager and you save the configuration to flash on that Ethernet brain, when you cycle power, your PID is going to come back up and running with the set point that it had when it was saved, the gain, the integral, derivative, the scan rate, and everything. And we're probably going to talk about this a lot more when we get to our advanced, because it is an important concept to understand the benefits of saving to flash and having a true distributed intelligent I/O. So at that stage, we come to the conclusion, and I now want to open it up for questions. You can ask any questions through the chat area. If you do have a microphone, you can put that in the chat area, and Alexi can unmute you, and you can ask your question via your microphone.
We do have a question for you, Ben. Earlier in the presentation, you mentioned that the Pack S controllers, they don't have PID loops. And our customer wants to know, if this is the only controller you're using, how can you add PID loop control to the process?
Okay, good question. What we have to ask is, well, what are you controlling your process with? The Pack S on its own can run 32 charts, and it has quite a lot of power, but how do you get the analog input into the Pack S? So I guess that's my question. In other words, it's very unusual for any Opto customers to use a Pack S with none of our I/O. If you're using a Pack S with our older legacy Mystic, then there's PIDs in the Mystic. If you're using the Pack S with our EBs, our Ethernet brains, or our SV, our serial brains, then they have 96 PID loops in them, and you can configure the loops in Pack Control on those EBs or those SVs. So In other words, it's very, very, very unusual to have a Pack S as an island, because a Pack S on its own doesn't have any I/O, so it has no inputs, no outputs. The best you could use it for is some sort of serial protocol converter, which means that it doesn't need PID loops. I hope you see where I'm headed with that. If you want to expand that question a little bit of how you would use a Pack S on its own without connecting to any parameters in your process, please feel free.
Yeah, I think that's a good question. It's a matter of understanding the architecture,
right.
And
yep.
Once you do, you realize you're okay there. Victor was asking for the formulas, and we will send you the presentation, Victor. A lot of these are also in the PID tutorial.
Yes, Form 1641. If you hop on our website, I'm sorry, I should have put that up. Form 1641 has all of the algorithms shown in there, and it also covers a lot of the material that I've covered today. What the P, the I, the D are, how to calculate the scan time. Some of the diagrams that I used were lifted from that document. So Form 1641, the SnapPack PID tutorial, is an excellent document. It's available off our website.
Great. Mike is asking, will the PID settings, the PID values, on my temperature controllers transfer to the Opto settings?
The answer is it depends. Obviously, it's going to depend on what formula your PID controller is using. Now, hopefully you've got a manual and you can look that up, and if it's the same as any of our velocity, B or C, ISA, interacting or parallel, then the answer is yes. So you could take those settings, configure the appropriate PID loop with the same scan time, and this is very important, it must have the same scan time in Opto as it does in your PID controller at the moment, because the integral is affected by the scan time. So yeah, you could transfer them across. If the formulas do not match, then the answer is no. So just that answers the question, but just to fill out everybody else, what they're asking is, we already have a physical PID controller, a standalone black box device that has an analog input and analog output, and maybe some sort of interface for being able to set PI and D. And so what the gentleman is asking is, how do I transfer those settings when I upgrade that black box standalone PID controller to the Opto system? And that's why I said, well, if you can find out what the algorithm is, and if Opto matches, and you can find out the scan time, then you can set up Opto, and yeah, you'll be able to transfer them across. Hence my answer, it depends.
Ben, there's another question for you. We've talked about how important it is to have the correct scan rate, and also the ability that each of the 96 PID loops can have separate scan rates, which is great. What are the range of acceptable scan rate values that we can enter in? How fast, how slow?
Okay, the minimum scan rate is 0.001 of a second, so that's 1 millisecond. 1 millisecond is the minimum. The maximum, you know, I've never, I believe it's upwards of about a day. I think we can go many thousands of seconds, which is just crazy. And you wouldn't have it that high. Certainly, upwards of 2 or 3 minutes is not out of the question. We'd be able to put that in there in seconds. Yeah, the scan rate is very important, Alexi, and that's why I took the time to explain it. Because you want the loop to be responsive, but you don't want it to be reacting to noise. And again, that's something we're going to look at in the advanced topic of how to set up your PID loop to take its input from a filtered analog input.
Great. Okay, thanks, Ben, and thank all of you for attending. Oh, I've got one more question, and then we're going to wrap this up. Victor is asking, the recommendation you make about the type of PID you use is based on what, or the default Opto? I think what he's asking about is the choice of the algorithm, and we've been recommending the velocity type B algorithm.
Correct. Yes, so that a set point change is picked up by the algorithm. The velocity type C doesn't see that set point change, and so it's not going to respond as well to set point changes. So yeah, and the default is the new type, that's the type B. If you have experience existing, Victor, with any of the other algorithms, then obviously go ahead and use them. Use what you know is the way that you pick which of the 5 algorithms that Opto offers you should use.
Okay, we're going to go ahead and wrap this. Thanks, everybody, and have a great day.